So good afternoon, everybody. I would like to announce our recovery lecture this Wednesday at 8:30. I will send to you an email, but I want to remind that I would like to recover the hour we lost past week on Tuesday afternoon, on Wednesday, excuse me, in the afternoon. And so I would recover that hour plus another hour in the first week. We also lost in the first week of this semester, in this fall semester. And however, I will remind you this. So after this 1 hour lecture, we have the next lecture the day after tomorrow in the morning at 8, from 8 to 10. And this is the time and the day you decided as the best one for you, for all of you, in agreement with your lessons and the other possible lecture you have in this semester. Okay. Okay, I will repeat this point at the beginning of the lecture in a few minutes in order to clarify to everybody this point after Salvatore Riccobono question. Frank. Ciao, Paolo, ci sono solo una cosa. Okay, uh, I want to start my lecture now, and okay, and I want to share with you my screen, and again I want to repeat my announcement. I have in mind to recover past lesson um the day after tomorrow on this Tuesday in the morning from 8 to 10. Okay, and um, we are concluding a very relevant part of our course because, as I promised to you, we are studying our elastic system in a very, very general point of view. We are considering structure and the aerodynamic operator, and we are representing the state of the system in terms of modal coordinate in time domain, or if you prefer, in Laplace or Fourier domain, in this equivalent way. And we are describing here the generalized aerodynamic force, modal force, because we are using modal coordinate, and in particular we are actually representing as a physical quantity the vector of displacement for the body, and this vector is represented as a combination of modal shape function like this and related modal coordinate q bar n this here. Okay, so this is our physical, and in particular we are representing the motion in a relative way by using the displacement, in the sense that these displacements are the elastic displacement. And therefore, if we have an aircraft like this, and we are currently considering this, for example, this deformation for the wing, and therefore, if we have this point, for example, this x point, We are currently representing the displacement from here to here by using this u vector, and we are this physical quantity, we are represented by this. So after this process, which is an essential process, the state is then represented by q bar, and we can forget the role of the physical quantity. We have only state space quantity like q bar. Okay. Now, what about this system? This dynamical system is a system having a set of external force like E external, and then internal force like given by the motion of by the aircraft. Okay. And at the end of this representation, we have a square m model diagonal mass plus in Laplace domain. We have this plus stiffness applied to the model coordinate in Laplace domain, and this is equal to E aerodynamic, which is a function of the displacement in such a way, and this is represented by this feedback branch, plus the external, okay, the external Laplace domain load. This external load for an aircraft typically could be the gust. So if imagine to have a gust profile like this. This is a vertical velocity given by gust, and this is the aircraft flying. If you have an aircraft flying and this aircraft is currently encountering this gust, the gust is something influencing the aircraft and is not influenced at all by aircraft aerodynamics. So this input is a true input. And this second term here is another term due to the fact that the aircraft is currently deforming during the flight, and the aircraft deformation is able itself to influence my deformation process as well. So the point is how this generalized aerodynamic force are dependent on Q, on the deformation state of the aircraft. This is the point we are studying in this phase of the course, and we have developed this part here essentially by assuming that this generalized force as given by the motion of the aircraft is composed by a dynamic pressure multiplied by a global generalized aerodynamic force matrix applied to Q bar. So we go in deep on this quantity, and we have decomposed this matrix ES by the product of four matrices like this here, this here, this E2, and this E1. And this decomposition for giving, this is a matrix product. So the order of this matrix is not changeable because of the unsymmetry of matrix product, and therefore we are defining this product in this way, so giving a role to E4, E3, E2, E1 by assuming this order in this multiplication process. And this is E, the total matrix, and we studied past days the following matrix like E4, E3 and E2. Today, I would like to complete this scenario describing E1. And I want just to give you a remind on E4. We consider yesterday, not yesterday, excuse me, past Thursday. And on developing E4, we projected, by definition, the generalized aerodynamic force. And I forget to emphasize the fact that here we have E bar, generalized coordinate. I have indicated this as E generalized coordinate as due to the aerodynamic of the aircraft. So EI is A, excuse me, just to distinguish this load by this load, which is the external load. Ok? And Luciano, scusami, ora sto facendo lezione. Ti posso chiamare tra un'oretta? Ok, grazie. Ciao, ciao. Okay, so we have this load term, true load term. It is not true load term, EA. Okay, in this decomposition process, we define, for example, this E4 like the projection of the pressure distribution on the n model shape function. Okay, we use the fact that the pressure is composed by a static portion of the pressure given by the pressure to the infinite plus this component here, which is the dynamic pressure, in the sense that this value is a time-dependent value. Okay, substituting this, we have this part here, which is zero, and the fact which is zero is the following. First of all, P infinite is not dependent on time and space, it's a constant, so out of the integral, and here we have the surface integral of the product n dot psi n. Remember that psi n bar is representing the vector field given by the mode shape. So you have to imagine please, a mode shape of the aircraft, for example, a bending one or a torsion one, okay? And assign for each surface point, because we have a surface integral, the displacement given by the mode shape, okay? If you apply the Gauss theorem, you have here to substitute this surface integral with the volume integral, volume in the body volume, in this case. Or, okay, you are in the boundary, and look, this boundary is a common boundary for fluid and body, but the vector field given by the mode shape is defining the boundary and into the body, inside the body, not in the fluid, because this is the mode shape. And so forth, and therefore, you may now apply the Gauss theorem not in the point of view of the fluid, but in the point of view of the solid. And therefore, this volume integral is a volume integral not in the fluid domain, but in the body domain. So involving the divergence of the mode shape displacement. Okay, and what is the divergence of a vector field? The divergence of the vector field, imagine the divergence of the velocity of the fluid. Okay, if you have the divergence of the velocity of the fluid, you have a quantity which is related to the capability of the fluid to compress or expand. Okay, if the divergence of the velocity is zero, the fluid is not, it is an incompressible fluid. Okay, you can apply the same concept for the mode shape vector field. If you have a mode shape for example, the first mode shape vector field, such that your mode shape is not indicating an expansion of a contraction of the body, not the fluid body, material body, then your divergence is zero. So you may distinguish two kinds of mode shape. Mode shape with zero divergence and mode shape with not zero divergence. What about the mode shape with not zero divergence? This kind of mode shape are the mode shape including something like breathing, expansion and contraction, hmm, of the mode shape, please, not the fluid. Okay. Typically, if you realize this, the typical mode shape of a wing structure is not compressible equal mode shape, but it's something such that the upper surface of your wing and the lower surface are moving in the same direction. So you don't have an expansion of your wing body shape or contraction, but you have just a deformation preserving a zero divergence phenomenon. Okay, so if you have zero divergence mode shape, this term is zero. Okay, that's all. And this is typical for body. Okay. Okay, so now I want to focus as a final part of our discussion. I want to focus on this operator. This is our last operator, and this operator is operator able to transform our modal coordinate vector into the normal wash vector. So we are looking for an operator such that on supplied to Q bar you have key tilde. Okay. So you want something transforming your Q bar, and Q bar is representing the deformation of the wing. You want something transforming the time varying motion of the wing body into boundary condition for the aerodynamic. So wall boundary condition, permeability conditioner, here represented by the vector Q bar. Okay, so we have to study this kind of operator. In order to do that, we have simply to consider the definition of this boundary, our boundary condition. In the left-hand side, we have V body dot n. In the right-hand side, we have key scalar quantity. It's a function of point and time. This is time domain, and this is the fluid part. Fluid. This is the fluid side, and this is the body side. Okay, and we have just to translate this relationship, considering that this relationship is a continuous relationship relating our body motion during the deformation. And in order to consider and study this, we have to consider how this quantity are actually transforming. In particular, look, V body is the body velocity. Okay, and so we have to represent this absolute body velocity vector. Any kind of velocity, body velocity or fluid velocity, are absolute velocity in air frame of reference. Absolute means air frame of reference, and therefore this V body is equal, if you consider this system, this is the aircraft, and you have a body frame of reference like this, X, Y, and zeta. This is body frame of reference. We have that this absolute velocity is equal to a relative component of velocity plus the motion of the body frame of reference. The motion of body frame of reference is equal to minus I u infinite. This is the motion of the body frame of reference, and we have to add to this velocity the relative velocity, and the relative velocity is u dot, because u is now representing the displacement, the elastic displacement of the structure with respect to the body frame of reference. This is a very key point. So this is a relative velocity, which is also elastic, no, better, flexible. Deformation, I don't know how to call this. However, this velocity is the relative is the flexible component of velocity. And this here, the other, is the rigid component related to the body frame of reference motion. I have to consider this decomposition for VB, okay? And therefore, we have for V sub B the following. We have minus I is this vector, unit vector I. So we have that the velocity, this transport velocity is minus I u infinite plus summation of psi bar r, for example, by q bar r function of t. Okay, this is a physical vector. Excuse me, this is a physical vector field, and this is a physical vector, this is a physical vector, this is a physical vector, the unit vector. Okay, so I have defined this. Now look that also the normal to the body is a time varying function, because when you are here at the beginning in the undeformed configuration, but in the deformed configuration you are currently here. And so you are here.
Sorry, Professor, this is Q dot, isn't it?
Yes. Yes. Oh, thank you. And so we have this. We have this. And this. And this. And this. And this. And this. And therefore, this point is moved from here to here. The distance between the black and the red bullet is exactly the displacement associated to that point. Okay? But we have also a normal here in the deformed configuration. And we have another normal for the same material point, but in the undeformed configuration. In this figure here, they seem to be parallel, but I want to improve my drawing. Okay, thank you. and we should have something like this. Okay, so we have an n in the present configuration for that point x, which is moving. So, and this is the normal in the undeformed configuration, and this is the normal in the deformed configuration. Okay. Okay. So we have to express this quantity and this quantity as function of our Lagrange variable of motion. The Lagrange variable of motion are the coordinate q bar. Okay. So how can we define the normal? We can define this material coordinate, the mesh line here. The mesh line here are line made by the same material. Okay, so the material in the black configuration is here. After, the material is in this other configuration. Remember that the motion is something like position. Now I have to reintroduce our material coordinate like xi alpha. Position x is equal to position in the undeformed configuration plus displacement u as a function of material coordinate and time. Now, I want to distinguish now the xi coordinate like xi1, xi2, xi3 with respect to the position x1, x2, x3. Okay. These two quantities are initially independent, quite independent, quite distinct. But in the standard practice, these two quantities are identified in the sense that typically the material coordinate are identified with the position in the initial undeformed configuration. And so this is the one of the key confusion for everybody. However, now I have to distinguish, and the material coordinate are now for me xi1, xi2, xi3. So for example, this could be, just to be clear, this could be the xi1, xi2 direction, the span direction could be xi2, the core direction could be this here, xi3, xi1, excuse me, 1, 1, 1, 1, 1, and xi1, xi3 could be the vertical, but we are not interested at the moment to a 3D representation of the body. We are interested on the surface representation. So the surface material coordinate xi1 and xi2. Okay. Now, if you take the derivative of the position with the, or the vector position with respect to xi2 in the undeformed configuration, you obtain a tangent vector to the material coordinate, which is defined like G0, 2, by definition. This is the definition of G2, 0. A G2, 0 is something like this, here, just here, tangent to the black material line. This is G0, 2. Okay? And in the same way, and the problem now is that we are considering a left wing, unfortunately. So let me orient this material line in the other direction, just for adding a normal, which will be an outward normal to the body. So let me define this direction for xi2 and therefore this vector should be something like this. This is G02, and this is G01, as defined like the derivative of the position in the undeformed configuration with respect to C1, G01. If you know the geometry of the wing in the undeformed configuration and you know this vector, you can easily define the normal as the normal, this normal in the undeformed configuration, like N0 equal to G1 cross product by G2 divided by the magnitude of this vector G1 cross G2. Let me do a comment on this local base vector. If you arbitrarily define your material coordinate in a very, very arbitrary way, so for example, stretching or compressing your material coordinate, so defining which is the 1 value, 2 value, 3, 4. Imagine to have a Taylor tape meter, okay, and put this on the wing and decide your scale for 1, 2, 3, 4. You are the boss, so you can define the scale. But because of the scale you are defining, because of that scale, this vector, the derivative of the position with respect to your x1 or x2 is something stretched longer or smaller, and this depends on the stretch you use. Of course, if you have equal spaced scale for your C definition, you should have something fixed, not stretched. But if, for example, the C scale is identical to the X scale for the position, you have the unit vector for G1 and G2. Okay? And therefore, you need to divide this vector product, this edge product or cross product. You have to divide this cross product by the magnitude in order to have a unitary vector, a unit vector, like the normal. Okay, so taking the cross product, you are sure that your N0 vector is orthogonal to the plane defined by G0 and G2, and then dividing by the magnitude, you are sure that this normal vector is a unit vector. Okay, so this is, ladies and gentlemen, we have obtained the normal. Okay, now we have to do the same in the deformed configuration. Okay, and you can imagine that the deformed normal, normal in the sense that this is the normal in the same point but in the deformed configuration, is equal to G1 cross G2 divided by G1 cross G2. But please note that these two vectors are now in the deformed configuration, and here we have G1 and here we have G2. You have in the red scenario here we have G1 and G2, and then the normal M. And what about G1? G1 by definition is again the derivative of x with respect to C1 plus the derivative of cross product with derivative of x with respect to C2 divided by the modulus of the vector. Now look x. X is the following, and for if you apply this definition, you have the derivative with respect to c1 as equal to x0 plus u, but u is summation of psi n psi r, excuse me, we use r, a function of x, by q bar r. Okay, and this is x, wedge product or cross product with the derivative with respect to c2 of x0 plus same quantity summation of psi r x q bar r. And you easily convince yourself that this normal motion, this normal dynamics, is related to the normal is related to the value of the normal in the undeformed configuration, and the value of the normal in the undeformed configuration is exact this term by this term, zero term by zero term, but you have also the cross, the mixed term, this multiplied by this and this by this, and you have also a nonlinear term, nonlinear with respect to q bar term. So you have this by this, which is a quadratic form for q bar. So we can develop this product, and by developing this product, we have, look, we have G0 1 cross G0 2 exactly by multiplying the derivative with respect to C1 of x0 cross the derivative of with respect to C2 of x0, and this is this term here, plus mixed term is something like the derivative of x0 by this product, by this, so we have G0 G01 cross product with summation psi r q bar r, and the other term is this by the other, so plus summation wedge G02, okay, plus higher order term, and the higher order term is the product of this by this. Together we have higher order term with respect to q bar. Okay, so I want to continue the other page here. We have that at the end of the story, the normal n function of x is equal to the normal in the undeformed configuration plus a term composed by that two term, which is the following, is composed by G01 cross product with the derivative of psi, so we have a summation here, r term, summation of psi r with respect to x2, and we have also the other term, we have two terms, and the other term is the derivative of psi r with respect to psi 1. Excuse me. Let me see. Let me do a check. This by this, this by this, and this by this. This by this, and this by this. Okay, and both of these two terms are equal to q bar, are multiplied by q bar, as you can see here. And however, we have also here, do not forget this amplitude. And here we should write the amplitude of this quantity. And you theoretically should include the same development we did for the normal in the deformed configuration. But here we're talking about the magnitude of the vector. And the magnitude of the vector is less perturbed by the single component of the vector by the deformation. So we could consider here directly this product, the amplitude of this quantity, but this is an approximation in the undeformed configuration. And we could include the fact that here we should write the magnitude of the deformed configuration, including this correction in the higher order term here. So at the end, we have the deformed normal is equal to undeformed normal plus a correction term like this. And this correction term is this quantity, which should be defined like a delta n vector, which is a modal superposition. Here, remember that here you have the modal coordinates. So you have n0 plus summation of delta nr by q bar r. And this is a function of time. This is related to the deformation, and this summation is summing the modal m mode, the modal component, plus higher order term. So we are talking about this point. We have a normal in the undeformed configuration here, and we have a normal in the deformed configuration. So we have this at the beginning, and we have this in the consequent time, and this is equal to, this is parallel, and this is the normal, and this is the delta n by, this is this difference here, like a, I don't know, a vector, and this a vector is exactly this vector here. This is a, and this is n0. Okay, so this A contribution is the contribution of the deformation on the motion of the normal. Okay? As normal to the body, and the body is moving. Okay? Oh, now we are ready for this. We are ready for this. And we're just to write the body dot n. So the body dot n is equal to minus I u infinite plus summation of psi r model shape, mode shape function by q r dot n0 plus another summation on modal contribution. I use another index just to not to be confused with this summation. These two summation are independent. This summation is building the body velocity. This summation is building the normal motion, the normal deformation. And we have delta n. This is delta n, please. This complicated quantity. Delta n p by q bar p time function. Okay, and this should be the normal wash. This is the body side. In the body side, we have the following. We have a steady component. The steady component is minus I u infinite dot. Let me write this way. We have u infinite I dot n0 first term plus we have the mixed term involving excuse me, this is q dot, this is q dot, the velocity. Okay, so we have this term by the n0 normal, and we have plus summation r summation of psi bar r dot n0 multiplied by q dot r, this by this, but we have also a term like this by this, so another linear term in the Lagrangian coordinate, and we can put together these two summation because we are counting in the summation the same quantity, and so we can include in the r summation also this summation here. I am talking about this point. We have, excuse me, we have a minus, this minus u infinite I vector dot delta n p vector and gain by q r plus higher order term. Okay, now look, we have expressed this quantity, which is the body dot n quantity, as a function of the motion of the deformation of the structure. We have a steady part here associated to the initial deformed configuration with respect to the flow direction, and we have a steady part associated to the motion of the aircraft, and this part is depending on q. Okay, so we are very, very, very close to the final formula for describing this relation between the Lagrangian state space variable and the downwash. Okay, we will complete this final part the day after tomorrow, and after this we are completed the scenario of the aerodynamic matrix, and so we have all the information for talking about the elasticity of general deformable configuration in general unsteady and compressible flow. Okay, and thank you. See you the day after tomorrow.